Hello out there. Let's bring up some good stuff here. Okay. All right. Let's come over here. All right. Come and say hello. Hello to you. Hopefully you're hearing me all right. And well, at least I know the chat works.
Yes, sir. All
righty. Thank you very much. I'll wait a little bit before I log into my math lab because I'll wait till I finish this section. Now it always gives me those warnings that it's about to log out, you know, if I don't pay attention to it. So let's see. Let's share us some screen and see what we got going on here today. So let's see. Are we looking at the normal distribution part 3? Hopefully.
Yes.
Wonderful. Thank you very much. So yeah, so we're going to do that in my math lab. And if you saw my Blackboard announcement, so if you were actually, you know, live for the lecture last week, I changed things. Not, you know, just a little bit here and there, the way I'm doing things. It doesn't mean that that lecture was completely invalid, but not by any means on principle. But you're going to see how I use the infinity a little bit differently now in the calculator. I thought about that after that class. It's probably good I didn't record that lecture anyway, because I would have just done it on Monday again. But that's the only difference you're going to see. But all the same concepts are the same, so it didn't affect anything like that. So now this section is the last section for exam 2, but I will be doing another section today. It's actually kind of related to this stuff, but they've sort of changed the format. We're now putting that on exam 3, and it used to be on this exam. It's just fine. That was what I'd said a while back when I had changed the review. You know, when I took some problems off of it, it was the problems for the next section. They're going to be on the exam 3 review when I get that ready. So, all right, so let's see what's going on here today. Normal distribution part 3. Now, last week we were the second part where we're doing those application problems where we were finding the probabilities of, you know, random variables taking on values in certain intervals, greater than, less than, between values. This week is kind of the reverse process of that, meaning if we have the area under the curve, or that, which is the probability, area is always probability on the normal distribution, can we figure out what the x value was that produced it? And we're going to bring back up percentiles. Like, for example, so we sort of know what percentiles are. We're going to work with them a little more in this section. But so let's say, I don't know, SAT scores, math scores are normally distributed and with a certain mean and standard deviation. So last week we would ask, okay, then what's the probability that a person selected at random scored more than something, greater than something, or between something? But what if we looked at it from this point of view? What if we said that you were told that your score was the 83rd percentile, could you figure out what the score actually was based on that information? And if it's a normal distribution, you can definitely do that. And that's what we're going to do this section. And I'm going to show you both chart and calculator. So, I'll bring that chart up right now too. So obviously, if you're just using the TI, you can use that. You don't have to do the chart, but I believe I've said last week that I can't just totally give up the teaching of the chart. But that doesn't mean you have to use it. So let's say find a z-score that has 59.10 distribution area to its left. And I sketched a picture down here. Sometimes the picture kind of helps, gives you a feel of what's going on here. And I'll come back up to what I have in writing there in my text here. Let's look at this first. So you see, if what's the z value going to be? So obviously, if there's 59.1% to the left, that's a little more than half. There's a 50% obviously in the middle. So I just kind of roughly drew somewhere to the right of the middle. It didn't have to be perfectly located, but just to give us an idea of 59.1%, which is an area of 0.5910. So last time, if we're using the chart, we would have calculated the z and then looked up that area. This time we're doing the reverse, almost like if, I recorded myself doing that and then played it backwards, basically, is what's happening here. So what am I saying up here? I call this, that's just what I call it, the reverse chart lookup. And you'll see when I go into the chart, we'll talk about the inverse norm in the calculator here in just a second. And let's see. So if we go to the chart, so instead of looking up the z, we are actually going inside the chart, and this is going to be on the positive side, and I'm trying to find 5910 or the closest thing to it. We'll talk more about that too, but I did these intentionally where they would be exactly on the chart. So I go inside the chart and I find it right there. See, last week that was a number we were trying to get. This time it's the number that we have. So then I look at that and I figure out what row and what column that's on. It's on the 0.2 row, the 0.03 column. So that would translate to a z value of 0.23. And then there we go. So that's the process. And I'll show you the calculator after I do this one. Now we're going to be mostly concerned with the left here than we are the right, but I did want to put one example here. Suppose the area was to the right. Because I just want to remind you now that, I shaded that. So you see 96.16 to the right is going to be, most of that curve is going to be to the right of your z. So your z is going to be sticking over there kind of far to the left, in the negative land. So, but remember though, if you're looking at the chart, you're not going to be able to find it by the 96.16%. You have to know what the area left is. Well, that's easy enough, because the whole thing adds up to 1. So if you know that there's 0.9616 to the right, 1 minus that will be to the left. So this little area in blue is 0.384, and then that's what I would look at on the chart. That's going to be on the negative side, 0.384. And where are you? I know you're there somewhere. There you are. Right there. It's in the negative 1.7 row and then the 0.07 column. So that translates to a z value of negative 1.77. So let's see. Back to the notes here. And now I'm sure you're excited to see how does this work in the calculator, right? So, and it does. It works in the calculator. Now, what I have there is the 83. I haven't put the more modern one in there. I guess I could attach it and repost the notes. I guess after I do this one, I can squeeze it in there below it. This is just what it looks like in the 83. Which I guess that's good that that's there so you can see it. Let me clear this out. There's all kinds of, so it's second distribution. It's the one right below normal CDF. So it's in that same location. It's just the one right there below it. Now this is utility area, so I'll do that first one, which was crud, I already forgot the number. 5910. So I'll put in 5910. Now because these are Z's, I'll put in 0 and 1 here. Now they've even made them more fancier with this left, center, right business. This is definitely area left. So you just leave that left. And then the Z is 0.23. So if you notice, and then I'll paste this back in the notes after I do the next one. If you notice, yeah, in 83, you don't need the 0, you don't need the 1, and you don't need the word left in there. Because the inverse norm function in the 83 is left. It only understands left. So this one you can actually get a little fancier with it, and I'll show you what I mean. But you're going to see when we're doing percentiles, it's only going to be left anyway. So it's very unlikely you need to even worry about it. Just leave it sitting there at left if you're using this calculator. And so there you go. So it's the same thing. And then the other one was after we subtracted was 0.0384. Yeah, that would be the left area. So I'm going to go second inverse norm. Inverse norm. So the normal CDF, 0.0384. Or I could have put in 1 minus 9616, or there's something else I even could have done. And there it is, negative 1.77. So I'm going to copy these out. And I'll put these in the notes and just repost these later, probably. But you see it doesn't really affect anything. All right, so I'll just kind of shrink that down there. Now, okay, I'll show you one more thing. I kind of almost don't want to show you this, but I sort of want to show you this just because it's there. But, you have to worry about this. But really, though, in this calculator, I could have done it this way. You're probably going to go, oh, I wish you hadn't shown me that. I'm going to do it anyway. It won't take long. Because mostly we're going to be doing right anyway, but because they've made the calculator more sophisticated now with all this business, I could have done this. I could have gone 9616. You can't do this in 83. You have to know left. But theoretically, I could have changed the word to right, and then watch what it does. It gives me that same answer. But since everything you're going to be doing is left anyway, it doesn't. Well, at least you will from test purposes. I don't think there's anything. Well, if that comes up in the homework, I'm still going to probably, so we're all on the same page here, I'm still going to probably translate it to left anyway, just so I'm doing it the same way for everybody. But I just want to show you that little feature was there, you don't really need it for anything, but of course now, let me go back and, well, I'll change it back to left whenever I do another problem here in a little bit, but it's probably better to leave it left, just that way it stays left all the time. But just wanted to show you just in case you were curious, we really don't need center for everything. All right, find a z-score given a percentile. Now, when we say a percentile, that means, so percentile means it's the percentage of scores below, or percentage of values below that number, whatever the case may be, no matter what you're referring to, like a child's height, or something. We talked about that example, I think, back in the percentile days. If your child's height's in the 73rd percentile, that means 73% of the heights are lower than at that particular age, smaller. But anyway, so by nature, percentile means left. There is no determination of left or right or anything like that. By definition, the word percentile will mean left. Because I think the way some of the wording in the homework is, it doesn't use the word percentile, and I believe I glanced at, there might be a couple of them where you have to realize whether it means left or right, but there's no doubt the word percentile absolutely means left, because left, in a number line, left means below that number. So let's say we're just going to find the z-score. That's what we were just doing in these other two examples, except we weren't just calling them percentiles. Now, here's where it gets a little interesting. Now, let's say, then it's usually common notation is to use a subscript there. And I believe I used that same notation earlier. We kind of just did a percentile thing real quick. We more focused on the quartiles, which are specific percentiles. But I did a couple of examples, just general examples of percentiles. We didn't spend much time with it, though. So how do we find the z-score that corresponds to each percentile? So we do that, if you're using a chart, you do that reverse table lookup process. So for 38%, that means 38, the area is going to be 0.38 to the left. Now watch what, I've got it snipped out for you here. Watch what happens when I go in here to the chart. I'm looking for 0.38. Uh-oh. I cannot find 0.38 exactly. You're going to have values that aren't going to be on there. In this case, the best way to do it, now on a test, it won't matter that much. It'll give you that, confident feeling of security, though, if you pick the right one, because you'll match the answer perfectly. Well, that's if you're using this chart. And once again, using the calculator, it'd be a little off. But once again, you would just pick the closest one. The best way is to pick the closest one to the number. So for 0.38, you look at these and go, well, 0.38 is like 21 away from this one, but it's only 17 away from that one. So I would pick this one. But like I said, it's not going to be, that much difference if you pick the other one, because you're kind of in the right area. But technically, we would pick the one that's the closest to it. But it's not going to be a tragedy if you don't. You just don't want to pick something that's way, off from it. So here's what so you see what I did right there. There are those two values. And so this is the closest. So if the answer, were two decimal places, we would pick, 0.31. Of course, I'll show you this in the calculator in just a second. Same one. Next one is for 72. So if you're using the entire chart, 0.72. Anything above 0.5 is going to be on the positive side. 0.72. Once again, here it does not hit it exactly, but it's closer to 0.7190 versus 7224. So we're literally looking for closest. It doesn't matter whether it's closest one below or above. In other words, this isn't the Price is Right, where you have to, your choice has to be the one that's closest to it, but lower, that you can't go over. You can go over here. You just want the one that's just absolutely the closest number to it. So this one happens to be the lower one here. 7190, that's in the 0.5 row and the 0.08 column. So your Z value would be 0.58. Oh, I've already got these in there for the new calculator. Okay, so I don't have to redo these again. They're already in here. So in the 83, you just tell it 0.38, tell it 0.72. It's going to give you a Z. the appropriate Z value. And here it is, the inverse norm, put in 0.38, change that back to left, and there's what it's going to spit out. Yeah, you might as well leave that there. There's no point in just going through. You could delete everything and leave it just like the 83 version, but that'd be kind of silly. Why do all that? You see it's producing the exact same answers. All right. So that's how you get your Z. Now let's see how you get your X values. Like I said, if we were doing the child's height or SAT score, that's how you get your Z. Let's see how you get an actual value that corresponds, an X value that corresponds to the value from a percentile. If you're doing this using the chart, you would use this formula right here. Now, all this formula is just a rearrangement, an algebraic rearrangement of this formula here solved for X. It's just already isolated and solved for X. I like that. It's already done, so you don't have to do it each time. I've helped people before, like in tutoring lab years ago, where their instructor didn't show it this way. And so they were always just setting it up like this and having to solve it each time algebraically. And I'd always tell them, well, look, you could just start with this every time if you wanted to. And they thought that was pretty slick, So they're, oh, my teacher didn't show me that. That's a little quicker, a little quicker and easier than having to do the algebra every time when it's already done. So the idea is if you're doing it this way, you're going to be in the normal distribution, you're going to be given your mean and standard deviation, and then you're going to have to find the Z value. And then once you have the Z value, you make this real simple from the percentile, and then you calculate the value from that. Now, there is a possibility a problem might give you the Z value, so be real careful. That's even easier. If it's not a percentile, like this first example, I'm glad we have this one here, is that it just gives you the Z values. So you don't have to do anything other than just plug it right in the formula. So stretch a roadway, mean 67, standard deviation 4. Find the speeds, which are the X values that correspond with these particular Z's. So there was no percentiles, they're already giving you the Z. So all we're doing is using this formula. And you can see the 67 and the 4 remain the same every time. And then we're putting in the 3 different Z's. So 1.96, which that in context, just to remind you that what the Z means, it's the number of standard deviations above or below the mean. So this means you're just about 2 standard deviations above the mean. You're going 74.84 miles per hour. This next one means 2.33 standard deviations below the mean. 67 plus negative 2.33 times 4 is 57.68 miles per hour. And if you're on the Houston roadways here, you better get over the right lane so you don't get run over. And the last one just means Z is 0. You were traveling the mean speed at 67 miles per hour. Ta-da! All right, I forgot where I got this problem from another book, so I don't know. I forgot. They posted their data source there. I forgot where it was. So, sometimes I make up stuff, but I didn't make these numbers up. So who knows how old the data is. But it's obviously based on a sample. You don't have the information for every male in the U.S. That would be a little impossible to collect. But hopefully they got a large enough sample. The larger sample, the better. And it's important that you diversify your sample also too, because I don't think you want to just collect data that would represent just a bunch of like professional basketball players or anything like that. But anyway, so they're saying the mean height was 69.6 inches with a standard deviation of 3. So assume the data is normally distributed. So that just a polite way that needs to be there means that we can do what we normally do, what we've just been doing here. We're going to find what we want to know what height represents the 80th percentile. So that means what height makes a man in that age range taller than 80% of others? And the next one says, What height represents the first quartile? Now, before I scroll down, I'm going to tell you something on this one. Now, this, you see first quartile. This might make you think, how we did that before with quartiles, where we had discrete data, where we had individual numbers and we broke them up into the median and split them in half. That doesn't work for this. So the way you would handle a quartile question is literally converting it to a percentile. We have to now treat that as the 25th percentile. We can't use our same, because we don't have like a list of numbers here. So that's how you would handle this one. So I thought that was kind of interesting for that question to be there, because it's a quartile, but it's not handled the same way as we handled quartiles before. So doing it this way, and I'm going to show you how to do this straight in the calculator. Yeah, I got it right over there, and I'll show you again here. Let's see. But anyway, we'll go chart here just to make sure. In fact, I'll just stay right here on the page of the chart. I won't even go to the other chart. We'll just look at it right here. I'll zoom in a little bit on it here. So we have the mean and standard deviation that is given to us. We just need to know the z that corresponds to the 85th percentile. Let me let's see. Yeah, okay. So come over here, and so what I would do is I like to identify which two values it falls between first. So it's between 7995 and 8023. I think we can clearly say that 0.8 is closer to 7995 than it is 8023. So I would pick that one, and then I would see what does that translate back to as my z? 7995 is in the 0.8 row, and then the 0.04 column. So it's 0.84. And that would be your z value. And then once you have that, you are in business, because you just use the formula. Your 69.6 was the mean. We just found that z of 0.84, and standard deviation is 3. That comes out to be 72.12 inches. So you're basically a 6-foot male, just a smidge over 6 foot, 0.12 inches over 6 foot, puts you the 80th percentile in that age group. All right. Isn't that terrific? Now watch. I'll just do this one in the calculator. No, it's sitting right there now, because I want to get that right off there. So what you do now? We go second, because you're going to see me do the inverse. I won't do it for the next one, but you're going to see me do the inverse norm again when we get to the homework. So you're going to see me actually type it in there. But I'll just do it for this one. So the area was 0.8. Now, so it's 0 and 1 if you're just looking for the z only. In other words, if I do this, well, I'll tell you what, I'll do it real quick. This is just going to give me that 0.84 number that I got from the chart, or close to it. Yeah, so there's your 0.84. But we can get the entire answer in one step by putting in the mean and standard deviation that was in the original problem. So now I put in 69.6. So whenever you want the z only, if you only want the z, so if I have a question on the test, and I often do, that says, okay, what's the z value corresponding to a certain percentile, and it's only asking for the z value, you would make sure that that was 0 and 1. If you're trying to find the x value, like we're doing right now, you put in the mean and standard deviation for the given problem, 72.12. Sometimes these are going to be a little bit off, but what makes this one pretty close is, when we look at the chart, it's 0.8, it's pretty close to 0.7995. So that's otherwise these may be a little bit off, but once again, well, I'm only concerned about the MyMathLab part. It won't affect you on an exam. Just pick the closest answers. Like I said, I will make sure that the answers aren't super close together. Hopefully it will do on the homework like it did in the last section. Well, that it will accept it for using the chart, or accept it using the calculator. We discovered last week, I believe, someone verified one way and I verified the other, so that was good. So hopefully that's the case here too. But on a test, just it'll be the close. Just pick the closest. If you do it right, there's no way you'll mess it up. All right, here I'm mentioning about the left business here. You know, yeah. So, but so the 83, yeah, if you only want the percentile value, the z, you just put 0.8. But you do have to put in 69.6 comma 3. But then you can just close off the parentheses at the 3 and not the word left. But you have to have the first 3 numbers in there, close it off. So if you got your 83 out, you can try that out and make sure that works. Okay. Yeah, I can't demonstrate an 83 anymore because I don't have access to the version of that online. But just it's everything but the left. So for the 25th percentile, oh, it looks like I don't have the chart. Oh, there. Okay, I didn't snip the entire chart. I just picked. Okay, I'll just go over here. So 0.25. Sometimes I'll just do that where I pick the 2 numbers that surround it. You know, that's usually good enough. But 0.25 is somewhere between those two. Oh, if it ends up exactly in the middle, I try to avoid that for exam purposes. But I think, I don't know what it's going for my math lab, though. Let's hope there aren't any that end up exactly in the middle. Once again, you could pick either one of them if you're doing this on an exam. I don't know what it would want on my math lab homework problem. You could pick, well, actually, hopefully it would accept the calculator. If you're doing it that way, it wouldn't matter. But anyway, if you're using the chart, I'm not sure what would happen. But long story short, 2.5 is closest to that one, a little bit closer than 2.483. So that's negative 0.6 row, 0.07 column. And then so it's negative there, see negative 0.67. So then you plug it in there, of course, same mean, standard deviation, and you get 67.59. And so if a male is 5 feet 7.6 inches, they were at the 25th percentile. And I won't redo this one in the calculator. Oh, okay. Here's one that maybe I didn't have to use the 83, but I might have used this newer calculator and just got rid of the left. But that shows the folks for the 83 how it should be entered. It's just see what's about the word left there. This is actually for the next problem. I'm sorry, but I still write syntax, but it's for the next problem. Why do I have that? That's confusing. I got to get rid of that. No. Well, I'll have to move this around a little bit. That's okay. Cut and paste. Sometimes I may repost these notes with just a little. If it's anything major, like the announcement I made about how I handle the infinity, I'll make an announcement about that. But stuff when I move a couple things around here and there, I probably won't announce that I changed it. But there it is. So for that one, and there's 67. So it's a little bit different, but not enough. Yeah, this one, I guess I didn't realize maybe I redid it. I didn't realize it was in 2 places. But I do want to keep the top one here and bring it down like so. And I can just reduce the ginormous font for that one. And so that way it's kind of showing you, contrasting the two and showing you, oh yeah, he was right. The word left doesn't have to be there. All right, let's talk about this one. Zoom back out a little bit. All right, suppose Geddy Lee was told in an accounting exam score was on the 90th percentile. The exam scores are normally distributed with a mean of 72 and a standard deviation of 12. What was Geddy's actual score? We'll say rounded to 1 decimal place. So in other words, 90th percentile, that doesn't mean we got 90% right. It could turn out that way, that would just be a coincidence. But it does not mean that by definition. It just means what score. It's a ranking, essentially, where 90% of the scores would have been below that and 10% would have been above that. So, all right, just want to give you an idea what it means. Okay, let's see. So there's the chart. So 89979015, clearly 8997. So if you're using the chart, it would be 1.2 row, 0.08 column. That's terrific. And then we just plug it right in the formula. So the mean is 72 plus the z value coming from that percentile, which is 1.28, times the standard deviation of 12. We get 87.36. So the instructions just said round it to 1 decimal place, which might seem kind of weird to round it to 1 decimal place, but it's funny. In my calculus classes, Lone Star, if I have exams that are, if they're not multiple choice, I'm grading them by hand. I'll often do that because, I may just pick the point values and I don't make them add up to a specific number. Let's say they add up to 130. So I'll just take the score and divide it by 130 and usually round it to 1 decimal place. Just, I don't know, just for the heck of it. So in one of those classes, somebody could actually make a score like that on my exam, theoretically. All right, let's see. A little tricky on the wording. Maybe I'm hoping this example will help us, will guide us as far as the homework purposes go here, So that's kind of why I'm glad it's there as much as anything else. Because when it says percentile, it's real straightforward. Here we got to think a little bit. All right, ice cream consumption. Well, unlike exam scores, I don't know if you'd want to necessarily be that proud if you were in the high percentile of this, but yeah, yay, I eat more than ice cream, more than 95% of people. Yeah, probably not something to brag about, I guess, but mean 15.4, standard deviation 2.5. Yeah, because the wording is a little tricky here, but once you see how what is the smallest amount per ice cream that puts you in the top 25? It means essentially the bottom number of the top 25. Now, I think a little sketch will help us on this now. So we're trying to find right there on that vertical line where you got the top 25 right there, and you're this minimum number that gets you in the top 25. Because what we're trying to do here is we're trying to convert this into a percentile. So we can't just take that 25 and read it and say that's 25th percentile. Because in this case, it's not the 25th percentile. It's actually the 75th percentile. Because think about this, if you're right there at that line where 25% are above you, that means 75% consumptions are below you, below yours. Hopefully that makes sense. So that's the wording. Anytime you see that will be the bottom. It says like the bottom of the top, basically, or the lowest, smallest of the top, bottom of the top, however you want to say it. It's 100 minus that will be the percentile. So we actually have to treat this as the 75th percentile. Oh, interesting, huh? Then once we realize that, the problem's easy. That was the hardest part, because if you're using the chart, you do this way. And so it's 7.75 is closer to 7486 as it is to 7517. And so the z value rounded to 2 decimal places would be 0.67. So you plug in, here's the mean, 15.4. There's the z value of 0.67. The standard deviation is 2.5. So we have 17.075. There it is in the calculator. Inverse norm, your percentile value, 0.75. 15.4, 2.5, comma, left. So notice the answers are a little off, but like I said, that's to be expected. Not necessarily every time, but Certainly possible. Now, how about the wording for the next one? What is the largest amount that's in the bottom 15% of consumptions? You know, what's the top amount of the bottom 15%? Now, that wording actually does mean percentile, because this is the whole bottom 15%. And then that would put you the top number of the bottom 15%. So that's the only way there's two ways these can be worded. You can't really say the top of the top 25%, because that would just mean whatever the maximum value is whatever the biggest number is. And you'd have to actually know the number. You couldn't really calculate it. Well, I guess if you did a 100th percentile calculation, you could do it pretty roughly that way, I guess. Or here, I guess, well, a 0 percentile. I guess you did something like that. But anyway, it doesn't really make much sense to do it for those. But so it's either bottom of the top or top of the bottom. So top of the bottom puts you at this line right here, which is the 15th percentile. So here's a table cut out. So where's 1492? There's 1515. It's closer to 1492. So we would go with negative 1.04 if you're doing it this way. And so it's 15.4 plus negative 1.04 times 2.5 equals 12.8. So it's 12.8 is the answer. And here it is with the inverse norm. Makes the only difference in the 83 is you don't need the word left there. 0.15, because that's your percentile value. 15.4, 2.5. Okay, pretty close. Not too far off. So isn't this fun? This will really be fun. We'll do this on the calculator, won't it? Here we go. All righty, here's a good business problem here, especially if you're in the food service industry, production, you know. Let's say you're the manager of the distribution line. Well, this would be distribution. This would be packaging. Okay, whatever the proper term is, you know, you're the manager of the packaging line here, where we're getting all these little carrots in the bags. Yeah, distribution would actually be the shipping and stuff, so. Alrighty, so bags of baby carrots, normally distributed with a mean of 32 ounces and a standard deviation of 0.36 ounces, which that's good that we have a low standard deviation, so that way it's pretty consistent. That needs to be as low as possible. Sometimes you have to wonder, you know, like in bags of chips and other things, you know, you kind of wonder what the standard deviation is, because sometimes it might seem like you get a bag of air, you know, versus a stuffed bag. But anyway, that's a different story. So we're going to say bags in the upper 4% are too heavy and need to be repackaged. Well, I mean, like I said, if this was a business class, we could probably, you know, discuss lots of issues there. But I don't want to get in a big discussion about it. But I could think of a couple of reasons. And because like I said, there could be more is what I'm saying. But I think a couple of them. One of them is, you know, maybe we don't want to give away too much extra free product there, right? You know, you don't want to give away too many extra carrots, could be one reason. And maybe another is the way the type of packaging. Maybe it's risk, you know, packaging, higher chance of the bursting, you know, upon the shipping process. I mean, you would hope it's not that fragile, but I mean, still, I don't know if that's probably lesser of a reason, really, but I'm thinking not too many bonus carrots is probably the real reason. So what are we saying? What's the most a bag carrots can weigh and not need to be repackaged? So I don't, you know, I've never been on a, you know, packaging line before, but I can only imagine maybe like the bags are going through, you know, and they might hit a scale. Maybe some sort of buzzer or sound goes off if the bag's too heavy, and then I guess somebody can grab the bag off there and maybe take it back to the beginning of the line again, cut it open. I guess, I don't know. Sounds reasonable to me. you don't just throw it. I would imagine you wouldn't just throw it away. You just need to put the carrots back in with the other carrots and let them get repackaged again. So anyway, so we want to know what's the maximum that it can get through that scale without sending off any kind of alarms here. So upper 4%. So we need to convert that to a percentile. So upper 4% means that 96% would be below that. So that's the value we're looking for. We're looking, the 96th percentile would be the value, that's the cutoff value. So if we're good, if we're at 96, or obviously lower than that, but this is the maximum, the 96th percentile. And then anything above that is tossed there. Now this one I kind of did it a weird way. I don't know. I may not leave it. Well, anyway, yeah, I wouldn't do it. I wouldn't do it. This I went ahead and just calculated the z and then put the z in the formula. That's kind of a waste of time since we already know how to do it all in one step right now. So this might make it more confusing. I'm going to get rid of that because I was just saying I was doing it as getting the z first, but now we know how to do the whole thing. So I think the 83 folks are going to, especially if you're going to be okay with knowing that it's the same thing just without the word left. All right, so not okay. I using the chart. I didn't even show the chart, but I'll do it now. 9599. I mean 96. Yeah, so actually 96 is right between those two numbers, but really close to 9599, which is in the 1.7 row and the 0.05 column. So if you're doing it this formula way, which isn't that bad of a way to do it if you have to. It's not that terrible. It's 1.75, and you just plug it right here in the formula. 32 plus 1.75 times 0.36 is 32.63. So you do it here in the inverse norm. 96.96, 32.36. Leave the left there. 32.63. And there we go. Okay, this is one that, well, I've already got the calculator part done. I can write this out if you want me to. I'm not going to save the work for this one, but I guess just in case somebody, I'll do a little sketch just to kind of give you a feel for the percentile part of this. But obviously, we're just putting the numbers in the calculator. You don't need to worry about me writing out too much here, but. All right, social media is 49 minutes per day, standard deviation 16. Times are normally distributed. What is the minimum amount of time spent on social media to qualify for the top 10%? All right, so what we have to realize here, the key on this is, and the only really key on this, especially if you're using a calculator, you don't have to really think too much here, is we have to make sure we understand that the wording there that this wording does not mean 10th percentile. That's what we have to understand. We have to understand that wording means 90th percentile because this. And as long as we understand that, we're going to have no problem here. Because if I recall correctly, I think that the answer is here. If you did 10th percentile, I think it's answer C. If you did 10th percentile, so that's why you got to be careful. So it's 90th percentile. So if you were doing okay, I'll do it real quick. Just at least I'll set it up. But the 90th percentile value between these two, it's closer to 8997. Oh, I'll come over and check that chat comment. I'll check the chat comment here in just a second. 1.28. Yeah, so then that's so if you're doing it this way, you would come up with 1.28. And then you would just say X equals 49 plus 1.28 times the standard deviation of 16. That's going to give you that number right there. Let's see. Here's what I'm talking about. So if this was a test type question, You see but you got to say, so there's an answer there if you do the wrong percentile. And I mentioned that in the normal curve last week. Even though I said the answers won't be close together, I just said, whether you use the calculator or the formula, I don't want you to miss it that way, but you could miss it like last week. You could miss it, let's say, if it was a less than probability and you did it as a greater than. That's a different story. Then you might miss it that way, but that's more of a conceptual mistake. But here, notice this, if you do it this right and you get this 69.5 and you do this correctly, then there's no way you're going to miss it, because this is the way I would like to have it, where the answers aren't actually close to each other. But like I said, I think C, if you do the 10th percentile, change that to 0.1 right there, I believe, I'm 99% sure that C is the answer there. So, but that's different. That's a different idea than rounding, or the difference in, let me see what the chat thing, make sure anything important here before I move on and see what. We don't do 10% because, as I just said, it's got to be based on area to the left, because top 10% means 90% to the left. That's why you want this to be based on left as percentiles. So you have to convert it to that. So that's why. Well, you could use that if I showed you that thing how to do. If you want to use that right thing in the calculator, you could do this 10%. But, I don't know why change that between left and right. That could make it more confusing if you ask me. But I would just stick to it being left and do it this way. It means, because you got to consider, like, the picture sort of shows why it needs to be, is why it's 90%. Because it's got to be what's, to be in the top 10%. Another way to look at it too, if you're going to be in the top 10%, your answer's got to be a number larger than your mean, 49%. So if you treat that as 10 percentile and you got to answer C, then there's no way that can be right logically. Because if you're in the top 10%, you're above that number. So there's another reason it's got to be that way. So yeah, that's another way logically you can look at it. So now you might, don't confuse this. Now I can see if you're asking that with where the second part of that ice cream problem, where it said the top of the bottom, group or whatever. That's different. This is literally the top 10% versus the top of the bottom. Okay, I can see where that would be a little bit confusing or whatever. But this is literally the top 10%. All right. There we go. Yeah, I think there might be something like this I saw in the homework. I wouldn't do this to you on a test, but it's kind of interesting to look at this. I like to show this because it's interesting in the fact of most people don't, 99.9999% of the population. When people talk about curving a grade, no one really knows what that means. Properly what it means. I mean, what most people think of curving a grade is really adjusting a grade. That means, adding points or doing something to it. That's not really what curving a grade is. This is what curving a grade is. And this is a lot worse for students. I wouldn't try to do this kind of thing, but I can see this kind of stuff being done like in, engineering courses and things like that. And maybe, I don't know, upper level medical school type courses, because a lot of engineering schools, I don't know what it is these days, the way it used to be, at least anyway, they'll make their exams like super hard, and the class average might be like 40 or something like that, because they intentionally make the exams hard, and then they can kind of control how they want the grades to go from there. And that's actually what curving really, really is. And for this one, this is really kind of rough here, because I never do any of this business, but it's interesting to learn, you're just learning what that kind of thing means. This one's really brutal because, 40% of the class is going to make a C on this particular final exam based on this kind of particular. Curves don't have to always be done in these percentages. They could even be done like 20, 20, 20, 20 or something like that. That seems at least a little more fair than this. This one's really rough with 40% in the middle being C's. 20, 20, 20, 20 might be okay. But this says that, the top 10% are receiving an A no matter what your score is. You have to be in the top 10%. So technically, so that, that may be above. It's really funny if scores were high because, which that actually curving wouldn't make much sense if the scores are high. But if they were like a higher grade distribution, you might, it might take like a 98 to make an A or something like that with this kind of method. If the scores were good, a 90 might not be good enough, but here it's going to be good enough. Anyway, so the top 10% means 90th percentile. So you got to be at the 90th percentile level or higher. So I wrote these out. So this is, and I have the results right down here. But I just wrote P90 for 90th percentile. So to the minimum A would be the 90th percentile. So it's this formula right here. Now for B, so the next 20% of the scores are B, which means 20 plus that 10, 30% are above the cutoff for the B. So you got this. So we're looking at the cutoff, the minimums for each of these distributions. Obviously, the maximum value for the B would be the one that's just right below whatever it takes to make an A. So that means 30% are above and 70% are below. So now you make it 70th percentile. So the next range, 40%, are this big block of C's right here. 70% so are above your minimum for C. 30% are below, so it's 30th percentile for a C. And then your D is the 10th percentile. So that's the minimum cutoff for the D. And then anything below that's an F. So here's each of the setups. This is the minimum. So your minimum score, I don't know, whether they're rounded or not. I'll just use one decimal place. But so it takes an 83.5 to get an A, 76.7 to get a B, 67.3 for a C, and then 60.5 is your minimum for a D. So that's really what curving grades is. You don't see that much, but certain situations, like I said, that's where you likely would see it in engineering schools. And generally, maybe with larger, fortunately, this school doesn't have ginormous class sizes. I've taught in large classes before at UH years ago. I never did this, but I've had some 150 person class. I couldn't imagine doing that for a Zoom meeting though. Holy cow, that'd be terrible. That'd be a nightmare. At least I can look at people, 100 something people. But anyway, so I think this, I don't know, maybe I was imagining things. I thought I saw something like this on the homework, but we'll see if that comes up. Because now we're finished. So now as far as this section, so I'm going to zip over. Now I'm going to wake up the homework here. All right. God, I hate when this thing's in my way and I can't get to let me shrink it down. Maybe that's the way. Oh, that's the way to do it. Shrink it down, then I can make it bigger again. Well, every once in a while I come up with a clever idea. So we want my math lab here. All right, come on, don't be so slow. Come on, log in. So this is now going to solve the situation of last week where we couldn't do some of those problems. I wish I could remember which ones I did last Wednesday, because between Wednesday and Monday, I don't know. I was hoping to do a fresh one, but it doesn't really matter if I do an old one or not. It'll be new numbers, because now we can do that remaining part of the problem we couldn't do before anyway. So that'll be good. So even if it's the same question, it'll still be useful. Because now I'm going to go and incorporate what we did last week with this week, both, so you'll see everything. So that'll be good. All right. Come on. You can do it. Here we go. Yeah, but I certainly want to look for anything I see that's really weird with these percentiles, like I was telling you about, that could potentially be weird. I can do a regular one kind of first, just to get our feet going, wet here and test the waters, so to speak. I didn't understand part D of problem 3. All right, let's see. Yeah, I mean, well, if you're talking about before, that's what I mentioned in my announcement. Yeah, we're going to cover that right now. You weren't expected to understand those parts because I had mentioned in that announcement, and I think I even said it during the lecture last week, even though I didn't record that one. But yeah, you weren't supposed to know how to do those. So yeah, that's what we're going to do. So you probably wouldn't have understood part D and a lot of the problems. In other words. I mean, unless you're just saying it is specifically part D just for this one and not the others. Oh, you meant this one? Okay, this wasn't a percentile problem. All right, well, I can tell you real quick how to do this one because I want to make sure I get the percentiles done. All right, okay, then I stand corrected. You weren't asking about a percentile. You were asking about this one, if I'm correct, the less than this or the greater than that, if that's the one you're talking about. That can... Oh, okay. Well, I'll tell everybody real quick. I mean, if you need me to do it, I'll tell you there's a really good example in my notes. So I'll just show everybody real quick for that one. Yeah, that's not a percentile problem. That is actually from part 1. You can treat that problem exactly like I did this example I'm going to show you right here. And we can come back to it maybe. If you want to come back to it after class, I'll be happy. This one right here. If you do it just like it, I'll be happy to do it afterwards if you want me to. If you treat it as 2 separate pieces, like I did here, and then add those pieces together. So I did them separately, and I added them together to get that result. That's exactly what that question is, that part D of that problem 3. So that I just want to, yeah. So there's how you do that. But like I said, if somebody wants to see that at the end, I'll be happy to do that. But I need to focus on the stuff that relates to the percentiles right now, and then we can come back to that later. Yeah, afterwards you can ask me anything, Monday I was helping someone with Bayes' theorem questions or whatever. Yeah, somebody said number 4. Yeah, this one we didn't do last week. Yeah, this one's got a lot of parts to it, I guess. So we can let me look and see if there was anything else here before I come back to that one that's got about 1 million pieces to it. Oh, wow. Okay. I did see that thing. That part D is the professor. Okay, they just did it for the top 10%. They didn't do it for every one of them, but yeah. We can come back and do this one too also, but I'll just go, just in case we'll see how our time goes, I want to at least tell you what's going on here. So you see, once again, the same logic that says professor top 10% of the class. So this is just asking a 90th percentile question. That's all it's asking. All right, so let's see. Let me look around a little bit here. Somebody has a request for the 4th one. Yeah, let's see. I guess it's okay. Ooh, okay. That one's got a lot of stuff. Okay, it's also 4D is also that question D is similar to the one that they brought up about the one I referred to from the other notes. Yeah, you have to do two normal CDFs on that one and add it together. So that one's a little tricky. So, yeah, I don't like the way these are worded. It's man. Well, yeah, it's kind of tricky on the percentile. You got to be careful. I generally don't use this kind of wording on a test here, but anyway, this is fine. We can take a look at this one because we didn't do this one last week for sure. So, well, we didn't do the part C or whatever. So, all right, let me bring up some fresh numbers here. Looks like there's only, yeah, okay, it's 2 percentile questions on this one, same problem. So this will work. So we'll probably just do this one entire problem and then go on break from there. Because I'll look through this. I'll look through all of these real quick and tell you. So, well, okay, let me do that right now, actually. Let me just show the completed. Okay, there wasn't one, wasn't okay. There's, all right, part D for that one's the same thing. I just want to address the percentile stuff. All right, 90% of the people consume less than how many gallons of water? Okay, that'll be a 90th percentile. You just treat that as inverse norm or the 90th percentile. We're about to do number 4, so I'll skip that one for right now. This one, 98% less than whatever. That's the 98th percentile. And I believe this one I've already talked about, just to mention that. So the top 10%, but that's the 90th percentile, not the 10th percentile. Okay, so at least I verbally covered the idea behind those. So hopefully that'll be good now when you try those, because you can at least go back and listen to me say that if you want to. So, but let's come back to this one, and this is the one we'll do here. All right, so let me uncheck this one because I don't want the numbers to be there because I want to make sure I get the check marks. All right. Distance per truck is normally distributed with a mean of 40,000 miles. Standard deviation of 12,000 miles. Complete parts A through D below. I think what I'm going to do here is, this seems to be the rule in most cases, but so I want to go, I don't sound too excited to do these problems. I'm excited enough. I just need more coffee or something, I think, here. I don't know. I'm perfectly excited. No, I'm excited. I'm just looking to see. Well, I mean, I wasn't excited about the wording on that one problem. Kind of bugged me because I don't like it because it's confusing, but that's the reason why I'm not excited about it. I'm worried about you being confused. Actually, it'll be this one, so you'll see it. I'm going to go ahead and go calculator route here. I think that's the best way to do this, and the way I'll treat this is, if you would like assistance with it being worked out using the charts and all that kind of stuff, maybe I can do it that way later at the end of class, or some other way to do this, because if I do them both ways, it has so many components, it'll take quite a while to do it both ways. Can we, I think, because usually we always have about the same number of people. It doesn't mean it's the same people every time, but usually, like last week, everybody seemed fine with just doing it in the calculator. So should I just stick with that for now and then help people individually that need help doing it the other way? Is that okay? Or let's see a couple of chats here. We'll see what we got here. All right, lots of yeses on the calculator there. So so keep that in mind, just because that doesn't mean I'm refusing to ever show you how to do it the other way. I'd rather just help you individually if you need it that way. Okay, I'm convinced now. Lots of it's a yes parade here. So yeah, and then but I'll help you. I'll help you if you're doing it the other way. It's just going to take longer. We can do this fairly quickly, and then go on break here. So All right, so, no, so this goes back to the normal CDF, and then now, so if you were attending last week's lecture, because I wouldn't expect you to rewatch the entire video if you were here, unless you wanted to, but now you'll watch me do the infinities the new way now. So this one, so this is between. Now we don't need infinity here. All right. We don't have to put these in thousands. We can just use the whole number, 24, because we're just getting probability answers here. Now, when we're getting the percentile numbers, though, I probably will have to put 1,000. I'll see how the wording's being asked here. But so I can use this as just 40, not 40,000. Either way would be okay. Mean 40, standard deviation 12. So we're going to go normal CDF. We're going to clear all this. So I'm not even going to cut and paste since I'm not doing any writing. In other words, you'll see everything I do right here. And I can always go back to it. This is between two numbers. So I don't need either infinity here. 24 and 40. Lower's 24. Upper's 40. Mean happens to be 40. That's delightful. And darn it, I already forgot the standard deviation. 12. All right, this should do it perfectly. Lower, upper, smallest, largest. I'm going to go with 0.4088. Got it. All right, well, you know what? Well, no, I can do this in the calculator without writing. Okay, this one is one of the ones where it's this two-piece thing added together, but we can do it. I went ahead and got rid of those notes. I should have left them up there. No, I didn't. They're still up there. No, it isn't. I deleted that part after I. It's actually this, it's this. So what you'll see me do is I'll do two of these and add them together. But I can do it in one step. One calculator thing here. So what is it? Less than 25 or more than 60. So here's how it would be if it was just less than 25. Okay, less than 25 is to the left. That means you're starting with negative infinity. Therefore, those of you that watched this live last week is going to see it different now. And, it's explained in the notes, but you'll watch it live. So negative infinity, I'm now doing it this way. It's -1. Second, and I actually put it in the notes. If you actually look at the notes, you can get away without watching the video. That's your new negative infinity. Frankly, because it's easier to type and it's easier to explain. Negative infinity, this is the upper is 25. Okay, same mean and standard deviation. Now, I can do one of two things here. This is not going to be the answer. It's part of the answer, but I'm going to be adding this to something else. So I can just go ahead and put a plus in here right now, plus, and then do the next one. There's no way on a test I'm going to ask you to do these where you have to add two of them together. There's no chance that's going to happen. Now, this one is a greater than. Let's see what it said greater than. I forgot. Or more than. More than 60. Anytime you do a more than, you start with your lower. Your lower is going to be the number, and then upper is positive infinity, because more than goes to positive infinity. So now I do 1 for +1, second EE, which is, so 1 EE to the 99 is positive infinity. Okay, so it's the same problem, so it has the same mean, same standard deviation. So that's the second part of this problem. But now I can just hit enter because they're already set up to be added together. So you see, that's the sum of the two. That's not just one of them by themselves. That's the sum of the two. So let's try 0.1354 and see how we did. Oh, percent. Okay, watch for that. 2 decimal places, no problem. Percent to decimal. So that'll be 15.34. Multiply it by 100. Yeah, it is possible on a test that your answer could be as percentages. Yeah, which that's easy enough. Just multiply your number by 100. So, all right. Now, this is tricky. To draw, maybe I will draw a picture for this one. At least 90% of the trucks. So it's not using that top and bottom business here. No, I'll go with this. That was the Bayes problem I was helping somebody with last week. It's 90% this way. In other words, at least 90% fall. Let me check the wording again. In other words, the number of miles by at least 90% of them, meaning that 90% of them will travel that many miles or more, at least that much. That's important because then we have to realize that the question is asking 10th percentile, not 90th. 10th percentile. That's what I was grumbling about a little while ago. But 10th, yeah, see, it's a little tricky. But now you know when you do it. Now, I like if I was going to do this on a test, I would use that, like the one about the curve grading or whatever. I would use, like I did in my notes, I would use top. Excuse me, I would say the top 20%. Because I've already explained that, like, say, top 20% means 80th percentile. I wouldn't use this at least wording on a test like this. Anyway, but now once we know it's 10th percentile, now it's easy. Now it's inverse norm. So now I do second, inverse norm, 0.1. I believe that's 40. That's 12. I didn't read what kind of answer it wants here. Let me see how it wants me to enter the answer. To the nearest mile. Okay, now it's okay. I could, instead of putting thousands in there, watch this. I can just go, or I can just move the decimal over either way. Yeah, I can just, that gets it into, so it was whole number, nearest mile, normal rounding. So 24621. So we didn't need to make it, to get the probability values, I didn't need this to be in thousands, but obviously now it's translating it to how many total miles. So I'm going to go 24621. Excellent. So then that's when I had to have whole numbers, or I could have put whole numbers in the inverse norm, but why bother? You see, I think it was just easy just to do it without them and then just do it at the end right there. What are your answers A through C if the standard deviation is 9,000? Okay, so it's not really anything. Oh, but the numbers are different here too. Okay, so no, it isn't. Same question. Okay. All right, what a waste. We just pretty much did it. I mean, at least give me, well, you know what I'd do here? I go second entry. I think I can second inverse my way back up to that very first one. Or second enter my way back up to that first one. Yeah. Change that to a 9. How about that? And I'll delete that extra 2. There we go. I'm going to go 4662. 4623. 4623. There we go. All right, 25 and a 60. So it just seems kind of weird. At least it seemed like you should, should change the numbers around a little bit more or something, but I got to go back one more here. And I got to remember, I'll change the 9 here, but watch what I'm doing carefully here. Because remember, this was two things added together. So I got to arrow back over and get the other one to be a 9 also. Yeah, right there. It would have been easy just to change that 1 there, wouldn't it? And forget that this had 2 parts. Now they're both 9s. 0609. So 6.09%. And then same thing, at least 90%, and then blah, blah. So all I got to do is second enter my way back to that inverse norm question. Right there, change that to a 9. Yeah, in this case, that second enter is a really nice feature there. And times 1,000, or you can just do it without, you can just move the decimal in your head if you want to. 28466. Ta-da! All righty, let me see real quick what's in the chat, if I'm missing anything important here. Okay, pretty much the yes responses here. So here's what we're going to do. We're going to stop there. We're going to go on break. I got 652. I don't know, 705. I don't know. One thing to keep in mind is what I'm doing in the next half is really the beginning of the material for exam 3. So yes, it's not going to be on exam 2, but it's absolutely going to be on exam 3. I just want to make that clear. And I'll still do, do homework from it, of course, too. So you will see that. So just want to mention that. So we'll just say we'll come back at 7:05. All right, I'll go ahead and pause the recording here so I don't have to edit it out later. Got to remember to hit start recording again whenever it's time, but I don't want to stop recording. I just want to pause it so I don't have to delete the gap later. So we're on break until 7:05. All right, I'm back. I did hit the resume recording thing here. Let's see what's in the chat before I get started here. Did you watch me do it when I did it? -1e. Then I also explained it in full detail in the notes. I put all the keystrokes. You need to go back and look again, but you just go -1 second, comma, 99. Or if you don't need the negative, it's +1 second, comma. If I copied the keystrokes and put them in the notes when I revised the notes and reposted them. So the EE thing is the second. It's second, comma. All right. With that being said, let's go ahead and move on here. I lost you on part B of number 4. Well, if you want to wait till the end, I'll come back to that. Unless it's something I can answer real quick. Oh, I probably can't because I've already done the entire problem, so we'd have to look at it again. Yeah, I think that'll take too much time to mess with now, so, but we can certainly look at it later. It's no problem. All right, so, okay, now let's go ahead and bring up the new section here. And always remember, you'll be able to go back and watch you could go back and watch this video with me doing the problem again also. So that's what I'm going to tell people in the future for this problem. If they ask me, I want to say, go to the video, and then I'll do it again live tonight, but I know Monday, of course, but after that, I'm going to say, go back and watch me do it exactly. That's the same thing as me explaining it again. So, but I'll do it one more time fresh. But yeah, but I'll get this video posted pretty quick. See, last week I had to use Monday's video, so it took longer, but I should have this video up by later tonight. So you can just scroll right back to that problem. So that's the advantage of problems the ones I picked to do in class, is you can specifically go back and see those done clearly. So, so you'll have that advantage for this problem too. So I'm probably going to do it fairly quickly. You want to do it a second time too, since it's a repeat. Then you'll have to ask me if there's something you're not sure about. All right, so sampling distributions and the central limit theorem. We're looking at, instead of distributions for random variable x, we're looking at now distributions of if the random variable is x bar, which x bar being the sample mean of a group of numbers. So in other words, let's say you take a population of how many numbers, you're taking samples of size 20, just different samples from that overall set, and you calculate an average, then you take a different 20 and calculate a new average. And then you're getting new variable values, which are x bar, like x bar equals this, x bar equals this, x bar equals this, so forth, so on. And then we're looking at how that relates to the normal curve and so forth and so on. Now, the normal curve, the central limit theorem, we'll talk about that. Well, I'm trying to figure out if I want to jump ahead here. Anyway, we'll start with this till we get farther down. It won't make much sense, but the central limit theorem, what we'll see here in a minute, is a very important and useful theorem in statistics relating the sample mean to the normal distribution. So now keep in mind, the sample mean is actually a variable value. Now, what you'll see, I mentioned about what I mentioned in words here, and I'll explain this, is why the central limit theorem is so important. It has to do with how x bar and x relate with each other. And it's from this first part of this definition. And this says if you take sample size of size n, where n is at least 30 from a population, so it's got to be 30 or more. The more the better, actually. But it can be from any population. And I'll show you a graph on the next page here, but it can be any population with a mean and standard deviation. It does not have to be from a normal distribution. It can be from anything. If you take all those possible x bar values from every possible sample that you could take from that population, it would plot out to look like a normal distribution, or close enough to being a normal distribution to where it's okay. We can treat it as a normal distribution. The greater the sample size, the better the approximation. So what makes that interesting is if you have some data set that is not normally distributed, you can then still solve probability questions as long as your variable is x bar, not x. You can find, for example, what's the probability that a sample mean is greater than something or less than something. 7.2 is not posted. Are you looking in the exam 3 notes? Yeah, there you go. It should be the only one that's in the exam 3 notes because it's the exam 3. That's good for everybody. I hope you may not realize that, but yeah, I know it's confusing because it just happened to work out where we went into a new unit, so to speak. So yeah, so everyone that wanted to look at their notes, it's in looking at these notes. It's in the exam 3 folder. So x bar then, as long as it's 30 or more, is going to be normally distributed. Now, all right, Now, part B says if the population is already normally distributed, then it doesn't really matter what the sample size for n is. In other words, the sample mean would be normally distributed no matter what. So, but it's the first part that really make the central limit theorem important. Before I come back up to these two things right here. So let me look at these little graphs here and show you that. So let's say for any population distribution, you see this is, it's hard to, it's blurry. I'll just tell you, but that's X. On the X-axis, that shows X. And you see that just looks like some sort of mountain range. That's obviously not the normal distribution in that picture right there, of course. But this says if you took data that came from this population and you calculate the means for sample size of at least 30 or more, and it has X bar on this axis right here, and you plotted out all the X bar values, they would plot out to be normally distributed. So that's very useful. Now, the only thing on the right on the graph is saying is that if it's already normally distributed, it's still going to be normally distributed no matter what. It's just the standard deviation is going to get smaller. Remember we learned last week that smaller standard deviation makes it narrower. I'll tell you why it's going to get smaller here when I scroll back up to the other page. You'll see. So it doesn't really matter what n is here. If it's already normal, it remains normal. This 30 rule only needs to be there as if your data is not normally distributed to begin with. Now this is going to be important, especially the standard deviation, not so much the mean, is anytime they give you a mean and a standard deviation in any problem, even for these kind of problems, they are giving it as its X from the distribution X. So then we need to know what's going to be the mean for the X bars, if that's what we're trying to find. So actually the mean of the X bars is the same as the mean of the X's. So they're identical. So the average of the sample means is the same thing as the mean of the population. It's kind of confusing with all those means and averages words thrown in there. But anyway, this is where it's important here. The standard deviation. The standard deviation of your X bar is going to be the standard deviation of your original, which even though it does, I just wrote the subscript X in there to indicate X, divided by the square root of n. That's why the standard deviation gets smaller, because you're dividing, that's why that graph got narrower, because we're dividing by the square root of n, so it's going to make it smaller. And this little phrase right here is also known as the standard error of the mean. So if you see a homework question or something comes up and says find the standard error, I think there is. I'll show you that when we look at the homework. It means this. It's easy. Just take the standard deviation, divide by the square root of n. But that's going to be important when we're doing our normal probabilities, that we take our standard deviation and divide by the square root of n. I guess that's probably to your advantage that this is not going to be on this exam too, because usually it is. So you have these mixed in with those other ones. So sometimes you have to pay attention about the dividing by the square root of n. But if this is already just going to be on the third exam, you won't have to, this won't even come up on exam 2. So hopefully that will make it less confusing. It should in theory. Because whenever this was on exam 2 in the past, that was the biggest problem students would have with this, is they were forgetting to divide by the square root of n on the standard deviation. All righty. Here's just, we'll get to some probabilities here in a minute. And here's just a general question saying, so records indicate average snowfall is a mean of 100 inches and standard deviation of 14 inches. Suppose the snowfalls are selected during randomly picked years. For samples of size 49, determine the mean and standard deviation of X bar. As I mentioned before, when you're given a mean and standard deviation in any problem, you can assume that's X. In fact, it'll be the mean and standard deviation of X. Always. But the question wants the mean and standard deviation of X bar. So where you have to be careful is not to fall into a trap here. It sure looks like all you got to do is go, uh-oh, I see the answer right there. I'm going to pick that. And that is not correct. The green check mark is correct. That is not correct, but it looks like it's certainly a trap for you to fall into for sure. That is not correct, because if you look back up here, the mean is the same. The mean is the same, but the standard deviation is not. The standard deviation of x bar is your given standard deviation divided by the square root of n. So I'm going to write that the mu of x bar equals the original mu, which is 100. So when you don't put a subscript next to it, that's assumed to be x. But the standard deviation of x bar is going to be the standard deviation divided by square root of n. It's going to be 14 divided by the square root of 49. Well, these happen to work out to be nice numbers, but most of the time you can expect them to be something where you need to use a calculator because there's decimals and stuff. But this just happens to be 14 divided by 7. I'm just telling you, numbers don't always come out to be nice and pretty like this, but they don't need to. You're using a calculator. But so anyway, so that's why it's answer A. Answer A is the correct answer. It's because the standard deviation of x bar, also known as the standard error, is 2. So when it comes down to doing, we get to this later on. Obviously now we know it's on exam 3, but we don't want to fall into that trap. We want to know that it's 2, not 14. So you'll still be able to do these probabilities in the calculator, but if you're using if you're using the Z formula and the charts, the only thing you have to be careful of is your denominator here. You have to take, well, so you're going to be careful in the calculator also. I'll show you what I mean in that. But just doing it this way, you're still going to have to remember whether it's calculator or formula to divide by the square root of n. So the key is the standard deviation divided by square root of n. Now here I'm mentioning the difference, which obviously this is really important whenever this was on the same test. It's still important, but when it was on the same test, it was really important to be able to, how do you know when it's x bar and when it's x? Well, first of all, you're actually going to have a sample size that you didn't really have. Your sample size was always 1 for these other problems. You were just choosing one thing. You weren't choosing a group of things. Like say, for example, choosing one house, maybe being in a certain price range, you might choose 40 houses. I can't even, I'm trying to think of the My Math Lab problem we were just doing. I don't even remember what it was about, but the trucking thing, wasn't it, or something? Or choose the one of them was trucking or whatever. If you suppose, what's the probability you take, one trucker and their miles or whatever. So that would not be this, this thing, because there's just one. But if you're choosing more than one, you have to incorporate the divided by the square root of n thing. And also the wording for these problems, it's going to say find the probability that the mean is less than, greater than, or between two numbers. The mean, not just the value of one thing. It'll be the probability that the mean is greater than or less than or between two values. So really, that's the only key to this is the Z. Is calculating the Z. If you get the Z right, everything else logically is the same. That's the only difference. Now this problem I did it for, both ways, if it was just doing this. So coffee machine dispenses normally distributed. So this is already normally distributed with a mean of 12 ounces and a standard deviation of 0.2. A sample of 9 cups is selected. So we don't have to worry about being more than 30 here or whatever, because it's already a normal distribution. So that's the key. So it's already normally distributed. So we're good there. So find the probability that the mean of the sample, in other words, you're selecting 9 theoretically, and then we're wanting to know what's the probability that the average of those 9 coffee cups is a certain, in this case, greater than 12.1. So for an average of 9 of them to be greater than 12.1, it better, you got to spit out quite a few good ones, in that sample to get more, since the mean is 12. So you got to get quite a few good ones for the average of that 9 to be 12.1 or higher. So if you're doing this, so it's X bar instead of X, and here's the Z, but you see the mean is the same on top as 12, but it's all about what's going on down here. So instead of just one number there, it's 0.2 divided by the square root of 9 cups. So if you're doing it the chart way, you would get greater than 1.5, and we learned last week. Yeah, so once you get to Z, once you get your Z, it's just how you get your Z is a little bit different. Greater than 1.5, and then you flip it over, and, it makes it negative, and you would just look up negative 1.5 on the table. So I'll do that real quick. So negative 1.50 would be right there, 0.668, and that would be your answer. And like I said, I was expecting that probability to be kind of low because, like I said, if you got 9 cups coming out there, because you got 9 cups, you kind of would expect normally some of them to be, a little above average, a little below average. But that was expecting a lot of them to be kind of above the average. So pretty rare chance that was going to happen. But you're going to see me do the normal CDF, obviously, in the homework. But since I already have this one here, I might as well just leave it. But look, so this one actually, I copied it over here. So it was greater than 12.1. So my lower was 12.1. The upper is 1e to the 99 for positive infinity. The mean is 12. Look at the standard deviation. You don't have to figure this number out in advance. You can go ahead and just type it in there like I did. In other words, you don't have to go 0.2 divided by square root of 9, then type that number in. Just put it in there as 0.2 divided by square root of 9. It'll handle it. So even in the TI calculator, you have to enter all the steps like this. So you put in the lower, the upper, and we did that last week. It's just the standard deviation is different. Lower, upper, mean, but the standard deviation is calculated differently now. It's the standard deviation divided by the square root of n. And there we go. Now, this next question would be as if this would have been asked in part 2 last week. What if we selected 1 cup and then we want to find the probability that 1 cup is greater than 12.1 ounces? So that you see the difference here. You're just dividing by 0.2 this time instead of 0.2 divided by the square root of n. But it's kind of interesting here. You could divide by the square root of n, but if n is 1, 0.2 divided by the square root of 1 is still 0.2. So you could actually use that square root of n for all of these, but you don't need to, whenever it's just 1. But so this one actually relates to last week. So this problem is one that, could be a exam 2 type question. So we just divided by 0.2 and we get a z greater than 0.5. We still flip it over like we would before. So it'd be negative 0.5. And it's right here, 3085. And to me, that makes sense. Obviously you don't have to think through this after you do it. I'm just sort of telling you this, but it does make sense that this is a higher probability. It's because you got a better chance that you're going to get, 1 good cup than you are if you take 9 of them, and expect an average of 9 to be that high, because like I said, with 9 of them, you got more, probably above and below. You got a better chance of getting lucky, 1 time here than you do 9 times, in other words. So that's why this probability was a little higher. But you don't have to realize that. You don't have to, that's not something you have to worry about being asked or whatever. But look at the normal CDF this time. Exactly the same except for the standard deviation. It's just 0.2 this time and not 0.2 divided by the square root of 9. That's the difference. All right, so weights in a certain fish are normally distributed with a mean of 11 and standard deviation of 6. If 4 fish are selected, what's the probability that the mean weight mean weight, in other words, the average weight of those 4 fish is between 8.6 and 14.6 pounds. Okay. So logically, it sets up like a regular normal distribution problem. Except now we have, once again, so the key wording here, and I'll highlight, this is the main thing right here. Probability that the average of that group. And here's what tells you that there's more than one fish being selected right there. So those two things together make it an X bar problem. If this was related to last week's stuff, this would say if a fish was randomly selected, or one fish, but obviously if you say a fish, that means one. If a fish was selected at random, what's the probability that the weight of that fish is between 8.6 and 14.6? That would have been last week's problem, or something like that, which could have been on exam 2. But this is what makes it newer material here. So here it is if you're doing it this way. If you're doing the betweens, you see that it's all about that denominator. It's 6 divided by the square root of 4, because n is 4. That's the key. So you convert both them to z. So on the chart, this is easy because you just look up. Remember, when it's between two numbers, there's no infinity involved or anything like that. It's just the upper value. So 1.2 is 8849, and negative 0.8 is 2119. So you subtract and get 6730. So let's look in the normal CDF. The lower is 8.6. The upper is 14.6. 11. 6 divided by 4. Square root of 4. 6 divided by square root of 4. Make sure that's in there. You got it. Well, so obviously this is 6731, but as I mentioned before, that's not going to be an issue. It'll be close enough to the answer you see on a test. Oh, let's see. I need to edit this problem one of these days. Study of the amount of time it takes a mechanic to rebuild the transmission for a 1992 Chevy Cavalier. I cannot imagine anyone wanting to rebuild the transmission for a 1992 Chevy Cavalier. At that point, I think you just push it off the side of a Grand Canyon or something. Well, assuming that there's no one down there. But anyway, yeah, I should change it to, which is not exactly a classic car. It's not exactly a 68 Camaro. Oh, yeah, they were functional little vehicles back in the day. But yeah, obviously, it's not something you want to waste any time. I'll just for a quick laugh here. They were just functional little sedan cars. But maybe I should at least make it something a little more modern. I'll put 1992, but I could just put any year. They were all the same. Yeah, I'm assuming most of you are definitely too young to even know what that. I mean, they weren't super. They were functional little vehicles. There you go. Chevy Cavalier. So I can't imagine anybody wanted to invest in some serious time and remodel. But anyway, all right. I'm sorry. Back to business here. But I should probably maybe modernize that a little bit. So, so it says 8.4 hours and a standard deviation of 1.8 hours. Actually, I could see maybe somebody that's training to be a mechanic. That could be like the car, use it as a training vehicle or something. So I could see that. Someone learning how to do it. If 40 mechanics are randomly selected, find the probability that their mean rebuild time exceeds 8.7 hours. Okay, exceeds just means greater than. But if you look at this question, notice that there's something that appears to be missing here. It doesn't say anything about the normal distribution, does it? That's kind of odd. Well, here's where the central limit theorem kicks in for us. Because n is 30 or more, in this case n is 40, it doesn't have to be normally distributed. We would assume that the sample mean x bar would be normally distributed. So let's say if the individual distribution of the times of the rebuilding the transmission were plotted, it might not be a normal curve. It might be some weird looking mountain range there, you know. But if you took the plot of different averages of 40 of them and plotted them out, then that becomes the normal curve. So in theory here, it would be, and I wrote that, I wanted to say that before I scroll down. So in theory, it would be wrong to do this problem if it would have said, if one mechanic is selected, find the probability that their time exceeds 8.7 hours, without having a statement in there saying it's a normal distribution. It would be not right to do it. In other words, you could calculate it. Yeah, you could get an answer, but it's an irrelevant answer. But here, it doesn't have to be. That beautiful central limit theorem automatically makes x bar become normal, even if x is not normal. Isn't that exciting? Isn't that terrific? That beautiful central limit theorem. All right, now that we've established that, we have mean is 8.4, standard deviation is 8.8, n is 40. Well, 1.8. I wrote it down, but I said it wrong. 1.8, n is 40. So greater than, definitely exceeds means greater than. So it'd be 8.7 minus 8.4 divided by 1.8 divided by square root of 40, which will round to be 1.05. It's a greater than. So I flip it over and change it. If I'm doing it this way, I would look up negative 1.05, which will be right here. So it will be 1469. There we go. But let's look at the normal CDF. It's a greater than, so that means when it's greater than, your lower number will be the number, the 8.7, then your upper number is going to be the 1e to the 99. That means positive infinity. So lower is 8.7, upper is positive infinity. There's your mean 8.4. But notice your standard deviation then is 1.8 divided by square root of 40. So we got to remember to divide by that square root of 40 when we do these kind of problems. Now, let's take a look at the next one. So it's basically the same thing the rest of the way here. Now it's just a matter, like I said, we'll do this in real time with homework here in a minute. But there's essentially no new ideas here. Unless they put something weird in the homework that I would not put on a test, then I'll show you how to do it. I'll do it, show you how to do it for the homework purposes. All right, red meat 196, standard deviation 22, sample of 50. I do not show anything for 7. I don't know what that means. Maybe you better I don't know what that means. Homework stops at 6.2. We already addressed this. It's in the chat right above yours. It's in the exam. Talk about the notes. The notes are in the exam 3 folder.
No, sir. I thought you were going to go on my math lab to do some homework problems. And
yeah.
it stops at section 6.2 on my math lab.
All right. Well, okay. Well, let's address that when we get to it then. Oh, okay. All right. Maybe. Okay. That's possible. Yes. Okay. Well, let me get to that when I get to it.
Okay.
Yeah, maybe I need to release that one. And maybe I didn't release it yet because it was exam 3, but I can do it. You know, I can release it. Okay, I believe you. I thought you meant the notes. All right, never mind. Sorry about that. But
no problem. Thank you.
we'll get to that as soon as I'm through with this, and we'll do that immediately. So that way you'll all be able to see it as soon as I open it then. So yeah, well, I might want to edit it though. So I might not give me a chance because in other words, I'll pick a problem that I know I'm going to keep, but give me a chance after class to go through it and look at it. I can't imagine you're going to be that excited to do these problems. Because I don't want to open them, and then because I open them and somebody does something, that means I can't get rid of it. But you can at least watch. You can at least watch me do it, and then let me add it, then I'll open it. Because there might be some bad problems in there I want to get rid of. But that way you won't be able to interact with me, but you can at least watch me do it. Yeah, and that's the benefit of the recording then too, because you better go back and watch when you do open it up. So, all right, so, Tyler, you'll be okay. Let's see. All right, less than 200. Okay, less than, that's pretty straightforward. So here it is, X bar less than 200. Here's all the pertinent information. So 200 minus 196 over 22 divided by root 50. And then if you're doing it this way, you get the z of 1.29. And remember, when it's less than, you just look it up as is. That's the one you don't have to flip the sign because the chart's already based on less than. So, all right. There it is, 9015. In the calculator is easy enough. There it is over there to the right. It's all about doing that 22 divided by the root. Well, okay, since it's less than, that means you'll start with negative infinity. So anytime you have less than, it's negative infinity. Your upper will be 200. 196 was the mean, and standard deviation is 22 divided by square root of 50. All right, so we're just about done with this in here, I think. So even until we go over. Got a couple more. Oh yeah, we'll do this problem in real time. I'll set this one up for you. Yeah, okay, finish that one. Assume the heights of women are normally distributed with a mean of 63.6 inches and a standard deviation of 2.5. If 75 are selected, find the probability that they have a mean and average height between 63 and 65. If the overall average is 63.6. Yeah, I would think this is going to be a pretty high probability. So let's see what we got. So we're between two numbers, 63 and 65. Here's the mean 63.6, standard deviation is 2.5, and a 75. So here's how you set it up if you're actually writing out the formula. So it's all about that bottom part, right? 63 minus 63.6 over 22.5 over square root of 75, and then 65 minus 63.6 over the same thing. Here are your two z's. I mentioned this in the notes last week. This may happen in the homework. I certainly try to avoid this on a test. But if you're doing like I have over here with the calculator, you're not going to care anyway. But if you're using the chart, and I mentioned if it goes off the chart, I could have really used 1 here. I just went ahead and used 0.999. You could have probably used 1. It would have been just fine. The chart shows 9998 at like 3.49, but so it doesn't matter that much. But if you're using the calculator, that's not even a concern, because you just put in the lower 63, the upper 65, 63.6, 2.5 divided by root 75. And then you see, close enough. That worked out just fine. That was beautiful. All right, let's take a look at this problem here that says packages of sugar bags for sweeter sugar have an average weight of 16 ounces, standard deviation of 0.3 ounces. The weights of the sugar bags are normally distributed, so therefore we don't care if the N is more than 30 or not. What is the probability that 9 randomly selected packages will have a mean weight in excess of or greater than 16.025 ounces? All right, this one's pretty straightforward here. So if you're kind of doing it the old-fashioned way here, nothing wrong with that by any means. So X bar is greater than 16.025. So you take 16.025 minus 16 divided by 0.3 divided by square root of 9. Oh, looks like I got. Yeah, all right. So then that gives you a z-value of 0.25. And then if you're using a chart, remember we do it this way. You do it as, remember if it's greater than, you flip it over and change the sign. So you would look up negative 0.25. And that's going to be negative 0.25, not negative 2.5. 4013. Well, there we go. 4013. And there we go. So, okay. So there it is working out that way. Let me insert the calculator screen for this one in here. Let's do that. So we're going to distribution, normal CDF. We'll start with 16.025 because greater than. So this 1 e to the 99 will be positive infinity. The mean is 16. And the standard deviation is 0.3 divided by the square root of 9. And let's see what that gives us. So let me snip this out of here. Put it to that in the notes. Right there. And I can reposition the notes a little bit later. I need to just drag this other part down. Actually, that won't be that hard to do real quick. Just grab. I need to be able, I got to get the whole thing in there. Just kind of drag it down the page a little bit. All right. And insert this in here. And we've got it. Here we go. 4013. How about that? Terrific. Now let's look at this question right here that says from the problem above. So we're still using the sweet or sugar deal. This is kind of a percentile problem. There is a 30% chance that the sample mean of the packages is above what value? And there's a couple of homework problems that are worded this way. So I went ahead and chose this wording. So 30% above. You have to be careful. You know, you can't just look at the percentage and assume that that's your percentile. You got to think to what it's asking. So I drew the little picture. 30% above means 70% below. So right here, 30% above, 70% of that's below. So in actuality, this is a 70th percentile problem. In other words, 30% will be above whatever that number is we get for the 70th percentile. And if you're using the chart, so 0.7 is between 6985 and 7019, but it's closer to 6985. So that means I would go with a p-value, a z-value of 0.52 here. And that's what I'll use for a formula. So so if you're using the formula, x equals mu plus z times sigma, no problem. So 16 is the mean, 0.52 is the z that we found. And so the only difference between this one and the normal distribution part 3 is now, instead of just 0.3 here, it's 0.3 divided by the square root of 9. That's the only difference. And I get 16.052. Now, so in the calculator, you do inverse norm, 0.7 for your percentile, then the mean is 16. Standard deviation is 0.3 divided by square root of 9. Of course, the left is just there, and then so you get 16.052. All right. So let's take a look at a couple of the homeworks then, and that'll conclude this section. That's it as far as the notes go, but jump over here to my 7.2. Now, by the time this video is published, the notes and the homework problems, I'm going to change them, some of them in and out a little bit, but not the one I'm about to do now, and probably not the next one I do, but there's some others in there I don't like. So maybe I'll keep it at 7 problems by tossing out and bringing new ones in. So at least that'll all look the same when it says 1 of 7. But this problem for sure is one that's going to stay. So like I said, you'll see the problem, but the numbering might look a little different when you actually look at the homework. But shouldn't be confusing. So let's see what we got here. We've got normal distribution with mean 104, standard deviation 15, and sample size is 9. What is the probability that X bar is less than 92? So I'm going to go with the fact that the folks that are listening to the show here, we've had this discussion before as far as vote yes to using the calculator for this, so I won't do this. You can come back to me later if you need the, the sort of written out, using the normal curve table, the chart and all that kind of stuff. I can show that to you individually, but I'm going to go ahead and go with what we normally do here, which is just using the calculator only. Obviously in my notes, I show it both ways, but for these, we'll just go calculator. So it's less than 92. So we go second distribution, normal CDF. Less than 92 means I need to start with the negative infinity, which is negative EE 99. And this was 92. Once I mess this up, we'll double check. Let me get the mean and standard deviation. 92. Mean is 104. Standard deviation will be 15 divided by the square root of 9. The n is 9. So the mean is 104. And then we have 15 divided by square root of 9. And I'm going to go with 0082 and see how that looks. Tremendous. There we go. Now the next one's between 92 and 95. Another nice thing about the calculator is it's going to keep the mean and standard deviation in there. So 92 and 92.5, I started talking, I forgot what it was. 92, 92.5, like so. So same mean and standard deviation, 0025. Let's see how that works. Well done. Above 104.4. So the lower will be 104.4, means it's heading toward positive infinity. So it's going to be 1 e to the 99. Four, 6, 8, 1. Perfect. Now this says 69% chance that X bar is above what value? So this is the same as the part added on after the sugar problem. Then the second part, we asked that same question. So it's just like this. And like I said, I told you I worded it this way on purpose also. So yeah, so that means the percentile will be 100 minus that. So 69%, so 100 minus that will be 31st percentile. So we'll use 31.31, obviously. So I'm going to go second, distribution, inverse norm, 0.31. 104, I'll double check this though. 15 divided by square root of 9. Let me double check if these numbers are right before I hit enter here. 15 over square root of 9 and 104. Yeah, that looks good. Paste. 101.52. Let's see how we did there. Terrific. I'm going to skip ahead and look at another one here, but like I said, this is going to change. I can already tell you there's one coming up here I know I'm going to get rid of and replace. Probably that one and definitely this next one. Yeah, this one's going to go. Yeah, some of these, I think I'm going to keep this one. We can give this one a whirl here. Let's try this one out. All right, I wouldn't worry about this part A being on a test here, but let me sort of tell you what's going on. This goes way back to where we talked about the skewing stuff, and this one, and because n equals 2, that means the central limit theorem doesn't apply here. And we have to use the fact that the mean is greater than the median, or the median less than the mean, which is the same thing. So by definition, that happens to be skewed right. It looks like I've brought this problem up a couple times before, so I think it's going to be this one every time. So I think it's just going to be skewed right for this particular problem. So I wouldn't worry about putting too much into this. This is not going to be on an exam. Not the third exam. No skewing questions. All right. Well, anyway, part B is kind of interesting. I like this problem because of this one, because now it says if your sample size is 100, this is where the central limit theorem kicks in. If your sample size is 30 or more, it becomes approximately normal or approximately normal either way. So the mean greater than the median that I just used for part A is irrelevant here. It's because of this sample size right here being more than 30. It's 100. It's normal. Okay, so I like that part of the question or whatever, but yeah, that's the whole idea behind the central limit theorem. So it says if you select a random sample of n equals 100, what's the probability that the sample mean will be less than 290,000? All right, so that's just going to be a normal CDF here. second distribution, normal CDF, less than 290. So we already have it. Yeah, this is the default here. So anytime you come back to this one, again, it has these, you know, if you've switched to another function, come back to this, it always starts out with that. So I'll put in 290,000 in here. All right, let's get the mean and standard deviation. The mean is 221. No, excuse me. The 221. Oh yeah, that's the median. Oh yeah, that was only used to answer that first part. We don't need this median anymore. The mean is 270,8. Yeah, the median, we don't need that anymore. And let me check the standard deviation numbers. It's 100,000, but it's 100,000 divided by the square root of n. Don't forget that. So it's 100,000 divided by the square root of 100. So he tells you, here's your 100 right here in the problem. So it's 100,000 divided by square root of 100. Like so. There you go. All right, so we got to be careful with that. So round it to 4, looks like 9726. Let's see how that is. Nine, 7, 2, 6. Yeah, I realize you can't see these homeworks at the time I'm doing this video live because I hadn't released them. So I'm going to edit them and then make them open. So by the time Monday class, we'll see these problems. And then what's the next one say? N equals 100 again. Now it's in just saying between 275 and 295. All right, so that's easy enough. Normal CDF, 270, yeah, 275, 295. And then the mean, and so n was 100. They could have changed the n if they wanted to, but they did not change the n, so it's still 100. So that means I can leave everything else alone. Let's try this. 3295. Let's see how we do there. 3295. Tremendous. That's wonderful. All right, so that's going to conclude the show basically here. Now I'm just going to stick around and see if you have any questions on anything, any of the homework, earlier stuff. So I'll get in there and fix these up and open these up. But once again, to remind you though that this section is only is on the third exam. It's not going to be on exam 2. But I do want to get them opened up. Some people might already be ready to try to work ahead a little bit. So let me edit them and get them posted up here soon. So, all righty, thank you. Hope you have a great week, and we shall see you again.